Hello friends, welcome back to the lecture series on applied statistics and econometrics, and today we are in the last lecture for the course. And in this last lecture we are going to see how the R software can be used to handle time series data and conduct econometric analysis involving time series data. So, let us have a look at today's agenda items. So, today we are going to discuss the classical time series analysis that we have studied in the first part of the course, and the second half of this lecture is going to be devoted to the time series econometrics, which we have studied in the second part of the course. And before I begin, let me make this cautionary note here. It is very important that all the codes that we are running in this R sessions, we are making use of R version 4.0.3. So, it may be the case that some of the codes that we are showing you here may not run in an older version of R. So, first we are going to talk about how to import time series data in R. So, for illustration I have chosen to work with oil price data. Of course, we all know that energy price and oil prices and petrol, diesel, every item that comes under energy basket of consumption is very crucial for economic growth, and it affects our day to day welfare as well. And nowadays we are all worried about the price hike in petrol, diesel and other energy products. So, I decided to talk about the oil price data over time, and let us have a look how over time, say 15-20 years, this price has evolved over time. Okay. So, I have downloaded a data set from the Ministry of Energy, Government of India, and it is a monthly data set, and we have crude oil price as the variable. So, I have downloaded data from Ministry of Petroleum and Natural Gas, Government of India, and I have data on crude oil price per barrel for the time period 2001 to 2019-20. So, we have a data set spanning over 20 years. So, it is a pretty large data set, and the level of the data set is monthly. So, the time unit is month. So, you see we have huge number of observations, and let us see how we can now import this data file which is in Excel in our environment. So, if you remember, we have to make use of that read Excel package, and that we have already installed. So, here I am showing you the code that first check whether in your machine you have that read Excel package installed or not, and how to figure it. You have to type this library within bracket read Excel command, and if it is there, then R will not object, and then you write this command that you are defining a data set that you name by oil, and for that you have to write this command read Excel within bracket. You see I am referring to the work directory, and then that Excel file is there in that working directory, and the Excel file name is priceoil.xlx. So, I am reading this data, or in fact I am instructing R to read this data in the Excel file and rename Excel file and call it by a different name, and that is oil. So, now if you write this third line in our command box, our console, that names within parenthesis bracket, then it will report you the variables that R finds in that Excel file. So, you will see in that Excel file I have only two variables, date and price, and R is actually reporting you these two variables only. So, now I assume that you have successfully imported your data into the R environment, and then we have to declare which variable is the time series, because that is very important. When you are dealing with the time series variable, you have to define that variable in the R environment as a time series, otherwise R will not understand that it is a time series data or it is a cross section data. So, you have to tell the software how to read the data and how to consider the data. So, here I am showing you the command which will actually instruct R to read a particular variable as time series. So, here you see I am writing this command in the box, where I am also indicating some important points of the command by red arrows. So, here you see I am now saying that I have to define a particular variable price as the time series. So, how to do it? Of course, you write this oil underscore ts and all, but note that there is a thing that you must remember when you are calling a particular variable from a data set in R. So, first of all you have to refer to the data that is defined properly in R, and then you put a dollar sign, and then you have to write the name of the variable when you are referring to that variable for statistical analysis within R environment. So, here we are interested in dealing with the price variable, and that is saved in the oil data storage in R. So, that is why I am writing oil dollar price in that code. So, remember that it is very important that you have to first give the name of the storage, then a dollar sign, and then finally write the name of the variable when you are calling a variable. And then you see the code is also showing from where the data begins. So, you see within this parenthesis after C 2000 comma 4 is given. So, what does that mean? So, 2000 is referring to the year 2000, and this number 4 is referring to the month of April, because we have the data from the month of April in 2000. Now, after that you see the frequency is mentioned, and this frequency actually talks about the number of observations per unit of time. So, R says that year is a unit of time, and for that there are 12 observations from 12 months. So, that is why frequency is 12. Now, in this particular slide I am showing you how you can draw a time series plot, but before you start time series analysis you have to install and call the time series package, and note that there is no typo here. So, after time S will be in capital, and then the rest of E, R, I, S will be all in small. So, this is the package. There are many other time series packages available, but for today's lecture all the calculations and plots I am going to show you, they are actually using this particular package. So, you remember that whenever you are doing some time series analysis, you have to first install any time series package, be it this one or something else. So, now I am showing you the command which you must write in order to plot this particular variable price across time, and if you write this command, then you get this nice looking plot. So, it is showing you how the oil price, crude oil price per barrel in US dollars has changed over 20 years of time. And now you see in the comment box you have this Y lab. So, that is basically asking you to provide something that you want to put as a label for the Y axis. It is not mandatory, and if you do not want to have a label for the Y axis, then you can omit this part. Now, let us quickly move to another issue, which is the decomposition of time series. So, we have talked about classical time series, and we have spoken about how to decompose a time series variable in 3 components, namely trend, seasonal component and the random component. We are assuming that cyclical component is absent in the data. So, now let us first start with the trend component and see how we can get the trend from a time series data set. So, in the R environment you have to make use of ggplot command which actually plots the data points, but even before that you have to first get this tidyverse package, and that you need to install. So, that is why you see very first I am showing you that thing that you have to install it, and then you have to search by tidyverse by writing this library command, so that you are double sure that okay, you have that particular package. Without that you cannot draw the graph. Now, here is the command ggplot, and you see here it is a lengthy command, but there is a reason why it is looking so lengthy. Let us concentrate on the first line of the command. There are 4 lines of the command, but let us now concentrate on the first line. So, here you see first you have to refer to the data set that you have defined in R environment, that is oil. So, that is there. Now, you are labeling the axis. So, the horizontal axis has to be labeled as say date, and the vertical axis has to be labeled by price. So, that is what I have written. Then you see the plus sign and the geom underscore point, this code is there. So, that will basically plot dots, and if you remember the last slide, I have shown you the diagram, and they were like line diagrams, but now you want the dots. So, for that you can make use of this geom point option. Now, let us move to the other lines. Note that this line is connected with a plus sign, that is a must. So, now you move on to the second line, and you see that I am now making use of a command which is fitting a linear trend line. So, here that is why I have written linear within bracket, and then you see in the third line I am now trying to fit a polynomial of order 2. So, a quadratic trend, and then I would also like to have a label for the fitted curve. So, I have written quadratic there in that code, and it is actually giving me a blue color quadratic curve fitted in the data. And what is the output of the second line of the command? So, here you see that there is a green color straight line upward sloping, that is the linear fit that comes from the second line of the command. And suppose I want to also fit a cubic trend, and similarly I can actually change the value from 2 to 3 in the same code, and if I do so I will get a cubic curve fitted to the scatter plot, and of course I can change the label for the curve to cubic, and that is what I have done here. So, I see a red color or orange color curve which is passing through the scatter point, and that is basically my cubic trend curve. We know that trend can be recovered or obtained by 2 methods. One is basically by fitting a curve that we have already studied, that is the curve fitting exercise that we have studied in the first part of the course. Now, we are going to talk about something that we have also studied in the first part of the course, and it also helps us to get the trend, and that is the method of moving average. So, now let us see how we can conduct a moving average analysis in R. So, here I am showing you the command that you need to write to conduct a moving average exercise, and you see that I am defining a particular variable oil SM3 as the moving average values, and then you see that I am using 3 periods for the moving average. Now, you may say that you have monthly data, why 3? It is just for illustration purpose. You can make it 4, you can make it 6, you can make it 12 also, it does not matter. So, just for illustration purpose I have chosen the number 3. But note that before you do any kind of computation and plotting of graphs, you need to install the TTR package. Okay, so, now we want to decompose the time series in 3 components: trend, seasonal and random, and let us see what can be done. So, if you remember, I have spoken about 2 types of decomposition, one is additive and one is multiplicative. So, here in this slide I am going to show you the codes for both of them. Let us first talk about the additive decomposition. So, if you want to follow additive decomposition, then you define a new variable, say oil underscore tscom, and that after that you write the decompose command, and it will decompose a particular data, and that data is basically oil underscore ts. Okay. Now, you see that this decomposition result will be stored in this oil TS_com. Actually it is not a variable, it is basically a data storage. So, after conducting the decomposition exercise on the oil price data, the software will generate 3 series of numbers, one for trend, one for the seasonal component, other one is the random noise. So, here these 3 components will be stored under this name oil_TS_com. Now, note that if I want to go for a multiplicative decomposition, the code will remain almost same, except for the fact that now you have to specify that multiplicative term in that command within inverted quotation, so that the software will understand that you are now asking for multiplicative decomposition. So, the default is additive. Now, as this multiplicative decomposition is conducted, another set of numbers will be generated for trend, seasonal component and the random noise. So, you need to store them again. So, now you have to define another new storage. So, that is what we are doing here. So, we are using the same formula decompose, but now we are saving the after decomposition results in a data storage, say oil_TS_com1. Now, you see I have also written plot oil TS_com, that will now plot the additive decomposition outcome, and now I am also asking R to plot oil TS_com1. So, that will now plot the outcome of the multiplicative decomposition. Now, let us have a quick look at the diagram that we get after running the plot command. So, here figure 3 talks about the additive decomposition and figure 4 talks about the multiplicative decomposition, and you do not see much difference in these two pictures, but let me ask you a very quick question. So, concentrate on the trend component of this decomposition. So, can you tell me what kind of a trend is this, what method we have used to get the trend values? So, here it is very evident from the graph that we have not fitted a linear trend line or a quadratic or any polynomial. So, what is it? It is fluctuating and it is not showing a smooth curve, right. So, we have actually applied the moving average method in order to get the trend component. And then you look at the seasonal component, it is showing seasonal cycles and the period is same. So, there is no irregularity there, and random noise is actually a purely random noise. You see that it is fluctuating around 0 mean. Now, after we have decomposed the time series, then what have we studied in part 1? We have also studied how to adjust a time series for seasonal fluctuation, and in R also we can write commands to generate seasonally adjusted time series, and that is what we are going to study next. So, here in this slide I am showing you the commands that you need to write in R environment, and R will give you the seasonal adjustment results. So, here you see what are we doing. So, first of all you need to define a new variable or a storage to save the seasonally adjusted time series numbers. These are all new numbers, and let me name that oil_TSADJ, and for that I am basically doing one thing. I have to now actually deduct that seasonal component that I just have derived in the previous slide from the original time series values, right. Okay. So, what I am doing? I am deducting this seasonal value of the decomposition from the oil_TS variable. Okay. Now, what is this? How can I refer that particular variable seasonal that I have stored? So, remember I have already spoken about this trick. So, first you have to call the storage area where you have stored the particular variable, then put a $sign and then name the variable. So, that is what we are doing here. So, we have saved our decomposition results for additive model in oil_TS_com, and after that we are putting a $sign and then we are writing seasonal, and if you run this command it will actually get the seasonally adjusted value. Now, similarly I can write another command or line in R for multiplicative, and then I can plot both the seasonally adjusted time series data. So, figure 4 and figure 5 are showing the seasonally adjustment data. Now, we are going to move on to the time series econometric part of the course. Classical time series we have done, and now we are going to talk about non-stationary data, how to deal with non-stationary data, especially in the regression context. So, we are going to start with a different data set. So, now onwards we are going to use a data set that is on India, and it provides yearly information on per capita carbon dioxide emissions and per capita gross domestic product from 1960 to 2000, and the data is coming from US Federal Reserve. And here I am showing you again how to read the data. Suppose in my working directory I have one Excel file named India 1, and I am calling that Excel file from working directory, and I am now naming that particular data file as India in our environment. So, again I can ask for the names of the variables that is there in this newly created data in our environment, and if you write names within bracket India, then it will throw 3 variable names to you, and these are basically the variables that we have here. So, ER, carbon dioxide and GDP. Okay. So, once we import the data successfully, we declare carbon dioxide and GDP data as time series as follows. So, again I am showing you the code in the box, it is a very straightforward code, and now you note that after you have defined these individual variables emission and GDP as time series variables, you need to combine them, and otherwise R will treat them separately. You can deal with them that way also, but later on when I will run regression and all, I need these 2 variables together. So, that is why I am combining these 2 time series variables in our environment by writing a command cbind. Okay. So, now after writing this cbind command, R will create a new data set which is called India_TS. Now, we are going to study the stationarity. I have already spoken about stationarity at length in the lecture. So, I am skipping a discussion here on stationarity. So, let us move to the R environment codes that you need to write when you want to check whether your data is stationary or not. So, how many ways a stationarity of a series can be detected? So, this could be done in 2 different ways. One is definitely visualization, and the other one is statistical test, and we are going to cover both aspects of stationarity checking of a time series. So, for visualization I am going to make use of autocorrelation function and partial autocorrelation function plots, and for statistical testing component or mechanism or technique, whatever you want to call it, we are going to cover only one test, and that is augmented Dickey-Fuller test. So, in the theoretical lecture I have already explained what do we mean by ACF, PACF and ADF test. So, I am not going to spend time here, let us go straight away to the codes. Before we run any code to check stationarity of the data, let us have a time series plot, because it helps to understand how the variables are evolving over time, and especially we are interested to conduct a regression analysis between these 2 variables. So, it is not a bad idea to see how both the variables are evolving over time. So, here I am showing you how you can plot the 2 variables. So, code is given in the box, and you see figure 6 and figure 7, they have plotted the variables for you over time, and you see that these both the time series are showing increasing trend, and there is a very smooth increasing trend over time. Now, we are going to talk about the autocorrelation function, how it can be used to check stationarity. So, for that first of all we have to ask R to compute autocorrelation function from the sample data. So, R can help us to draw the sample autocorrelation function diagrams, which are in theory called correlograms. So, we can generate correlograms for both variables by writing this command, and you see I have written this command ACF, and I am naming the variable, and then I have indicated the maximum number of lags that is permissible. And here you see I have talked about 8 lags, but it can be 10 also, it can be 4 also, it does not matter, it is an arbitrary choice from my side. So, anyway, if I choose a lag length of 8, then for 8 lags it is presenting the autocorrelation function values for both variables. So, now you see in figure 8 we are getting to see the sample ACF for the series emission, and you see that there is a slow fall, you can call it an exponential decay in the values of the sample autocorrelation functions over different lags, and you see these horizontal dotted lines in this box. So, they indicate 5% significance limits. So, if you see one spike or one bar at one particular lag, the falling outside this horizontal dotted band, then actually for that particular lag ACF value is statistically significant, and if the spike or the bar lies within this horizontal dotted band, then you say that statistically it is not significant. So, for all practical purpose you can assume that ACF value is 0. Now, note that I have spoken about one theoretical result, that at 0 lag the autocorrelation function will always take value 1, and let us see whether that is fulfilled by data or not. So, if you look at the diagram, see at the 0 value of lag the autocorrelation function takes value 1 for both the series. So, it is fulfilled. Now, you look at the figure 9, which is the sample autocorrelation function for GDP, and here also you see that there is an exponential decay or a very slow decay of ACF values that is shown in the correlogram. So, from the correlogram for both the variables, what can we infer? So, it is obvious to us that we are dealing with non-stationary data, because in the case of non-stationary data it will show such exponential decay kind of a pattern. Now, we are going to talk about the partial autocorrelation function, and I am showing you the command that you need to write to generate the graph for partial autocorrelation functions, and you see I have plotted partial autocorrelation function for both series, and now you see why partial autocorrelation function is so important. And let us first look at the emission series. So, you see there is only one spike which is lying outside of this horizontal dotted band. So, you can say that here there is only one spike or only one PACF value which is significant. So, you can say that I can model this non-stationary data with an AR1 process, because from the sample PACF we get to know the value of the P parameter of the ARIMA PDQ model, right. So, here you can say that as there is only one spike in this PACF diagram, then I can go with an AR1 model. Let us look at the GDP case. So, here also the partial autocorrelation function shows a very big spike only at one lag, and all other PACF values are insignificant, they are all lying within this horizontal band. So, we can assume that here this series GDP can also be modeled with an AR1 process. Now, we are going to look at the stationarity test by following augmented Dickey-Fuller test, and here I am showing you the results for both the variables. So, you see that in order to compute the test statistic for augmented Dickey-Fuller test, you require one package called ATSA to be installed and downloaded, and that again you can check from library whether it is properly installed or not. And then you need to write this command stationary.test within bracket India dollar CO2. So, we are testing for stationarity, and that is why this is the comment, but at this point I would like to draw your attention to one point, that this is not the only comment that you can use to conduct augmented Dickey-Fuller test in our environment. There are many other comments, and in this lecture only later on I am going to show you another comment which is useful to conduct augmented Dickey-Fuller test. And why is this so? Why we are having different comments? Because R is a free software and there are many scholars who are interested in writing their own codes and then making it public for the greater good of the society, and if they write a particular program and if they are thinking of a name and that is already taken by someone else, then they take a different name and name their code, and that is why you will see that there are several packages in R, there are several commands in R which will do the same thing. Okay. So, now within bracket we are writing India dollar carbon dioxide and India dollar GDP. I hope you remember what I talked about. So, you have to first call the data and then put a dollar sign and then you have to call the variable. So, now you have a look at the augmented Dickey-Fuller test statistic values for different lags and the corresponding p values. Okay. Now, there are 3 different cases reported for each of the 2 variables. Now, the case 1 is no drift, no trend, and the case 2 is with drift, no trend, and the third case is with drift and trend. Now, we know what trend we are talking about. Trend, of course, we know, but what is drift? So, basically if you have a constant term in the regression, that will actually create a drift. So, I do not know whether you remember, I have spoken about this thing, although the original Dickey-Fuller test does not contain an intercept, but if you wish you can actually throw a constant term in the regression problem, and then correspondingly you can get your coefficient test statistic values and all. Similarly, for ADF also putting this intercept term is not mandatory, it is optional, but if you put that, that will be called a drift. Okay. So, now we know what is drift, so and we also know what is trend. So, now let us have a look at the results. So, you see for all cases, be it presence or absence of drift and trend, the p values are very high, almost equal to 1 for both the variables. So, what does it mean? So, p value is so high means that you are failing to reject the null hypothesis. And what is the null hypothesis for augmented Dickey-Fuller test? Do you remember? So, null hypothesis in this context is H naught is delta is equal to 1. So, that means that there is unit root, and if unit root is there, if you cannot reject that null hypothesis, then that means that the data is non-stationary. Actually, the data is difference stationary. So, you have to take difference and then you have to make the data stationary. So, now as we know from the augmented Dickey-Fuller test for sure that we have a difference stationary time series to deal with. We have to take first difference, and here I am showing you how you can do that in our environment. Codes are shown, and finally you see that the first difference values for both the variables can also be plotted, and I have plotted them, and you see that smooth trend that we have seen in the initial plots for the level values of the variable now has disappeared. Now, there are zigzags, although there is mild trend in that zigzag for both the variables, but overall you can say that they are looking like a more or less stationary process. Okay. So, after we have plotted the time series plot for the differenced variable, let us investigate that difference series by looking at their ACF PACFs once more, just to be double sure that we do not have non-stationarity problem. So, we have generated the graphs for the first difference variable. So, the first difference variables are defined as d1 underscore emission and D1 underscore GDP, and note that again you have to maximize, you have to report, you have to set some maximum value of lag. So, we are setting that equal to 8 like previous graphs comment, and again the ACFs are showing up. So, here you see that there is only one large spike at 0, and after that at 3 there is a significant spike, but it not that high, and if you look at and that is basically for the case of emissions variable. And now if I look at the case of the GDP variable, we see that only at 0 there is one big spike, but no other spikes have gone out of this horizontal band for any lag. So, you see for GDP we have a clear cut case of stationarity. In the case of emissions there is small problem at lag 3, but as the value of the ACF is too small, we can ignore it. We can say that okay, emission is also difference stationary. So, now let us have a look at the partial autocorrelation function to be double sure. So, here you see for the case of GDP I have figure number 16, and you see none of the PACF values are lying above that horizontal dotted line. So, they are all within that horizontal dotted lines band. So, it is a good news for the GDP variable. So, we have stationarity, and for the case of emissions you see only at lag 3 we have one spike which is slightly above that horizontal line, but it is so small that we can ignore for all practical purposes, and you assume that okay, emission is also stationary. So, you can write the same command again and conduct the augmented Dickey-Fuller test. Statistically you can check whether the differenced variables are indeed stationary or not, and here you see I have written the same command, only I have changed the name of the variable. So, no need to spend more time on this slide. So, now we believe that we have two stationary variables and we can safely conduct a regression without falling in the trap of spurious regression, and I am going to show you what sort of a regression we can conduct with this difference data. Now, note that you have created two new variables which are basically the differenced data. So, you have D1 underscore emission storing the data on differenced values of emission variable, and then you have D1 underscore GDP which is storing the values for the differenced GDP. Now, you need to combine them. These two variables D1 underscore emission and D1 underscore GDP are time series variables, but they are treated separately in our environment. So, if you want to run a regression you need to combine them, and then you use the cbind command to combine them in one data set or storage. Okay. And now you name that particular data set, and for that you have to write this data dot frame command, and suppose you give it a new name India 1. So, if you remember the previous name was India with which we have started our analysis, but now we are creating India 1 because now we have a new data set which is differenced data set. Then of course, you know how to run OLS regression, you have seen the command. So, you have to write this second line command, and you of course will get the summary reports of the regression, and I have already explained different blocks of the regression result. So, nothing new here for you. You see that this D1 GDP is significant, and intercept term is also significant. So, overall F statistic has a very low value of 0.01. So, although the R square is quite low, but as the F statistic is significant, we can say that regression is meaningful. So, once the regression results are obtained, what to do? I told you after running time series regression you still have to check for residuals whether they are white noise, they are stationary or not. So, now we are going to spend a couple of minutes on residual analysis. So, now here I am going to showcase two different issues. So, first suppose you run your regression by following textbook. So, you first make your data stationary and you work with the differenced data. So, you then regress the differenced values of emission d1 underscore emission on the difference values of GDP. The name of the variable is d1 underscore GDP, okay. And then you generate the residual and that is stored as res1. And suppose now I want to ignore what is being told in the course and in the textbook. So, I want to run the regression on the level values itself, knowing that my level values, the variables emission and GDP, they are non-stationary. But suppose I ignore that wisdom and then I just want to conduct the regression, and of course, you will be able to get some residual values, and that is basically known as that is actually named as res, okay. And now you are going to conduct the ADF, the augmented Dickey-Fuller test, for both residuals coming from the level value regression and coming from the differenced value regression, okay. So, here you see that now I am making use of ADF dot test to conduct augmented Dickey-Fuller test, and you see here I am showing you the first case where the regression is done on the level values, okay. And you see that for most of the cases the p values are very high, and in some cases you see low p values, but none of the ADF test statistics are significant at 5% level. So, basically we can say that the null hypothesis cannot be rejected. So, that means that there is stationarity and unit truth. And now if you look at the ADF test on res1, so which is the residual generated from the regression using difference data, then you see you have lots of low scores for the p value. So, that is good news for us. So, then for most of the cases you can actually reject the null hypothesis, and you can say that my residual that is coming out of the difference data based regression, that is stationary in nature. Okay, so this is it for the time being on R, and this is the last lecture. I have only 5-10 minutes left in the course. I can't teach you something new. I wished I could show you something on Excel, because I understand that this R that I have shown you for last 3 lectures may be complicated for some of the audience who are not that tech savvy and who have not used software in their college days. So, it may be a bit difficult to handle R. Now, there is an alternative, and that is Microsoft Excel. Microsoft Excel also can do wonders for you, and you can not only conduct statistical analysis using Microsoft Excel, you can do little bit of econometric analysis as well. So, I end today's lecture by showing you 2 books, and if you wish to learn to conduct econometric analysis by using Excel spreadsheets, then I suggest that you should have a look at these 2 books. So, there is an excellent textbook written by R. Carter Hill, William Griffiths and Guy Lim, and the title of the book is Principles of Econometrics, and that is an undergraduate typical econometrics textbook, but for that book there is an Excel companion. So, this is developed by G. Briand and R. Carter Hill. So, the name of the book is Using Excel for Principles of Econometrics, and in this book the authors have shown you how you can actually execute all the regressions and econometric analysis that they have discussed in the main textbook Principles of Econometrics using Excel spreadsheets. So, these 2 books are quite complementary in nature, and you should have 2 books together, so that you can make the best use of this book on Excel. So, this is it, and I wish that you have liked the course. I do not know how much of knowledge is transferred from my side to you, some topics I have covered pretty fast, and maybe there could be some more illustrations from my side, but I worked under stipulated time slots and hours, and within 30 hours I think the coverage that I have provided is good, and at least this will educate you about different dimensions of econometric and statistical analysis, and if you are interested to pursue advanced statistical and econometric analysis, then you are most welcome. I end this course by saying that never ever be afraid of data and statistical computation. If you can bear with it for maybe some initial days or initial months, then data will be friend with you, and it will do wonders for you. Thank you.